Welcome to our final project, Neural Networks for Cardiac Event Prediction. My name is Bhargava, and I'll be accompanied by my teammates Michael Silver, Daivik Dhar, and Zijin Zhou. In this presentation, we will go over the introduction, data processing, our model architecture, provide a live demo, and we'll finally discuss the results at the end. So cardiovascular disease is the leading cause of deaths worldwide. So far, current technology is too late in predicting when these events will occur. This is where our project comes into play.
The database we will use comes from the real ICU data from the MIMIC database, which includes heart rate, breathing rate, RESP, and blood pressure ABP mean recorded every second. We want to convert this data into a format which we can use. The data came in different files, one file for the numbers, one for alarms, and others for machine messages. At first, the data were all in binary, not a readable format, so we used Python tools to turn it into clean tables we could work with. The AI model's architecture requires us to split the signals into 2-minute slices. Each became a CSV file with 120 rows and 3 columns, HR, RESP, and ABP mean. For every slice, we also made a TXT file that listed all the alarms that happened in the next 2 minutes. In the end, we also made a full list of all the alarm times that showed up in the dataset. Above said, this is our actual workflow with the data processing. Once we got the raw data, we applied a layered cleaning process. First, we filtered out extreme values that were beyond human physiological limits, since these are usually machine glitches. Then we used interpolation to smooth the signal and restore it where possible. We also split the data into 2-minute windows and removed any windows with too many missing or zero values. After that, we matched each window with the alarms that happened afterward, so we could use them as prediction targets. So ideally, we will transform this noisy and spiky raw signal into a clean, smooth, and continuous signal to use.
Our ICU dataset faced 4 key issues: noisy signals and poor documentation. Filtered by psychological thresholds, missing values, filled with Python-based linear interpolation, ambiguous event labels, grouped into broad medical categories, and severe class imbalance. Over 90% no event labels addressed with class weighting to prevent realistic patterns. Moving on to potential improvements, we can improve by using advanced imputations for nonlinear trends, wavelet-based denoising for cleaner signals, semi-supervised or expert-guided label refinements for realistic synthetic data to boost rare events, and hybrid balancing that combines class weighting with target oversampling.
Now, going over our model architecture. We process ICU data into sequences of 5 consecutive windows, each with 117 timestamps and 3 features. Each window goes through a CNN block that extracts short-term patterns using 3 convolutional layers with batch normalization and a ReLU activation function, followed by pooling, dropout, and flattening. A fully connected layer with softmax then gives the current prediction. The CNN outputs from all 5 windows are then stacked into 5 feature vectors and then fed into a 2-layer LSTM, which captures long-term trends. The LSTM output then predicts the next unseen time window, when the hybrid combines CNN feature extraction with LSTM temporal modeling for accurate, timely cardiac event prediction.
My name is Michael, and I'll be presenting the live demonstration of our hybrid model. Displayed right now is the PyTorch implementation of our model, of which you can see the CNN connecting to the LSTM. Now here, I have 3 different matrices representing different patient types. Each contain physiological ICU ratings corresponding to different event types. The first is a normal person, of whose ideal outcome should be no event. Second, contains symptoms of apnea, which should be the predicted outcome. Finally, the third contains symptoms of someone experiencing missed heartbeats, of which the outcome should be, again, missed beats. Now, if we use our test model evaluation function, we should be able to see model behavior. So if we input normal person for the first one, our output looks great. We get no event for both model outputs. Now, for the second one, apnea person, we see that, again, CNN and LSTM both output apnea because it's one of our higher accuracy events. Finally, we'll put in our missed beat patient. We can see that our LSTM, while it correctly predicts missed beat, the CNN does not. We attribute this to the short time window that's being implemented into the CNN as opposed to the long time windows that the LSTM deals with. This is predicted model behavior. We'll now be moving on to our quantitative results. Let's start off with our training data. We can see that accuracies start and end very high. which is due to the huge class imbalances since most people will not experience a cardiac event. However, we still get a noticeable accuracy increase as well as plateauing loss curves, indicating we reach the max performance in our model. Looking at class-specific accuracies, we can see that some events have a significantly higher accuracy than others, but similar distributions in the dataset. We weren't exactly sure why that was, so now let's move on to our quantitative results to figure out why. Looking at these confusion matrices and comparing our knowledge of cardiac events, we can see why these event balances occur. Essentially, the model confuses events with similar physiological signals. For example, key symptoms of both tachycardia and ventricular arrhythmia are an elevated heart and respiration rate and dropping blood pressure. Unfortunately, it's hard to distinguish between these with the available data, so we leave this task to future works. Looking at the binary matrix, we can observe that our binary event/no event classification does extremely well, which may actually be a more effective case of the model rather than multi-class classification.
Takeaways start with the importance of robust data processing methodology. Clean, consistent ECG data is critical for reliable predictions. Next, our model demonstrates balanced performance and strength across different cardiac event types. We also see the value of cross-device and cross-population generalization, ensuring that our model works well on different hardware and for diverse patient groups. Finally, a seamless integration with clinical workflows is essential so that our prediction can be acted upon quickly and effectively in real-world healthcare settings. As a team, we've truly enjoyed working on this project and look forward to advancing it through the next steps toward real-world deployment.